really what we're trying to teach with MEAs and through problem solving is higher order thinking skills, and this isn't necessarily specific to math. Mathematics doesn't have a monopoly on higher order thinking. Certainly, we have mathematical thinking, but scientific inquiry is sort of the scientist's approach to problem solving, and then within the field of engineering, we have engineering design. And in other disciplines, we have critical thinking, or maybe historical argumentation would be how each discipline would phrase their specific approach to problem solving. Well, there's one other which is gaining some attention within certain fields, and that is computational thinking. And this would be how a programmer would approach problem solving. Now, all of these overlap, and the place where they overlap, as I've said, is in their approach. It's their discipline-specific approach to problem solving. So I think we're probably familiar with mathematical thinking, so I'd like to focus a little bit on computational thinking. So what exactly is computational thinking? Well, the consensus is not really set on what the definition of computational thinking is. There was a report done by the National Research Council on a workshop on computational thinking, where some of the leading thinkers in the field of computer science and computer science education and math education discussed aspects of computational thinking, and they came up with several definitions. You can see some of them here. My way of approaching it is, as I've said, it's the way a computer programmer would approach a problem, and it really tries to answer the question: what sorts of things can be computed? What sorts of things can we calculate, and then how do we go about calculating those things? In particular, if you look at that second definition, computational thinking focuses on the process of creating and managing abstractions. That could just as easily be a definition for mathematical thinking. There is agreement. Although there wasn't agreement on exactly what computational thinking is, there is agreement on the fact that computational thinking should be a core skill in citizenship in schools. So just like we teach literacy, we should teach computational thinking. So the question then is, if computational thinking is something we value and something we think that students should be exposed to, then how exactly do we teach it? One approach can be called computational science and engineering. Computational science and engineering is more about how can computers and algorithms and computational techniques be used to solve scientific and engineering problems, and for that matter, mathematical problems too. So here's some tenets or some quotes about what computational science and engineering is from a paper by Yasser and Landau from 2003. And in that paper, they pointed out that, according to the National Science Foundation, computational science and engineering is an appropriate pedagogical approach for science and math education. All right, so what is computational science and engineering? Well, it's sort of it's evolving, and we see here that this old view of computational science and engineering is that it was the intersection between math, applications to science, and the computer programming or the hardware and software, and where all three of those met. This view is evolving over time, and we're beginning to see that computational science and engineering is sort of taking on its own life. This idea of developing these tools for scientists, mathematicians to use in solving their problems is taking on its own life, and it's actually beginning to form a bridge between the application of mathematical principles and the math itself. So, again, referring to Yasser and Landau, they listed some important student learning outcomes that one should gain from a computational science and engineering course. And if you look at these, the second, the third, the fourth, and the sixth could just as easily be math objectives. So you can see the parallels between computational science and engineering and the math that we teach, especially the math as described by the Common Core standards. Okay, so we have these parallel fields, computational science and engineering and mathematics, which have similar goals, and the question is, can they complement each other? Can they work together? So what I want to know is, can we use computer programming as a learning tool? And the answer seems to be that there is some evidence that the answer is yes. So an early pioneer in this field, Seymour Papert, wrote a book called Mindstorms, which I'm not citing directly here, but the approach he described was summarized in the NRC conference on computational thinking. By programming the computer to do interesting things, children become highly sophisticated and articulate in the art of developing models and developing formal systems. Another member of the conference, the NRC conference, said that programming can help students to break a big problem into smaller problems. Just in theory, programming does seem to have some potential as a learning tool. Now, there is also research to back up that this can be a successful approach. Hatfield and Kieran did a 3-year study of some 7th graders and some 11th graders, and they found positive gains on the computer programming group in both groups. And what they said, basically, in completing the task creating a computer program, the students end up learning the material more deeply. In this way, students begin to see the computer not just as a calculating tool which can work out basic arithmetic for them, but actually as a problem-solving tool. The question for me then is, can programming be married with model-eliciting activities to create educational and research tools to elicit student thinking? If we compare the definition of programming given by Fertig and Papert in 1968 to the definition of model-eliciting activities given by Lesch and Zawadzki in 2007, we can see that the similarities are striking. There's clear overlap between the process involved in creating a program and what Lesch and Zawadzki have defined as a model-eliciting activity. All right. So let's take this again. We had those 6 principles earlier of a model-eliciting activity or designing a model-eliciting activity. Can programming fit those definitions, or can programming tasks fit those definitions? Well, the first question was model construction. Well, the algorithm that you create in creating your computer program is the model. So MEAs must be based in reality. That's easy enough. You just have to take your program and give it a real context, just like you do with a regular model-eliciting activity. Self-assessment, this one is one I think which is really powerful. In programming, in order to get your program to run or to get your program to work, you have to debug and you have to error check. And that is exactly what we mean by self-assessment, to go through and check, does this work? Is it doing what I want it to do? In a traditional model-eliciting activity, students must do that sort of in the abstract. In a computer program, that's done a lot more concretely. The debugging actually happens. The program either works or it doesn't work, and it either gives the answer you expect or it doesn't give the answer you expect. Model documentation is key in designing model-eliciting activities, and in computer programming, it's always important to document your code. Models that are created must be shareable and reusable, and that's a fundamental idea in computer program, that your program will be shareable and reusable. And the last idea is effective prototype, and this is teacher dependent. If a teacher creates or a researcher creates an appropriate programming challenge, then it can satisfy the effective prototype requirement. In my mind, then, these computer programming challenges can actually act to bridge the gap between the concrete and the abstract. And in discussing the model-eliciting activities, Lesch and Harrell noted that the most difficult part is to make the connection between the symbolic descriptions and the actual real world situation. So we have, on one hand, we have the concrete real world situation, and then we have our symbolic representation, which is the task of the creation of the model. So in a programming challenge, the programming code, it forms the bridge between these two. And here's how. The program is concrete because it's executable. You can hit enter and the computer will run and it will tell you if it worked or if it didn't work. On the other hand, the code itself, the syntax and the semantics of the code itself, is a symbolic representation. So we have a connection between the symbolic representation and a concrete result that can help in this model construction. Okay, so how could we design a computational model eliciting activity, which is my term for the marriage of computer programming with model eliciting activities? Well, it's simple. The product is just a program, a computer program. So I have some rough examples that I've thought of. The map app, where students need to write a computer program to calculate the area of irregular shapes. And this would get into decomposition and Cartesian coordinate systems. And then another one, cargo conundrum, where students would have to write a program to determine the number of types of arrangements for shipping containers on a barge. And this one would get into factoring and prime factors and counting the number of factors of specific numbers. Okay, so now that I have this idea for computer model eliciting activities, it leads me to my research questions. So the first question, in what ways do MEAs elicit mathematical and computational thinking? The point of these is to work on or to study and develop and cultivate these higher order thinking skills, this mathematical thinking and computational thinking. So I want to know, in what ways does that happen when students are going through an MEA? And that leads to the second question. How do students' conceptions of a specific mathematical concept evolve throughout the course of a CMEA? And then the next question, which would sort of happen after these first two have been not necessarily answered, but at least explored on a first go-around, is, do CMEAs allow students to make connections between the abstract and the concrete? Or in other words, will abstract concepts transfer to different concrete situations? The idea being that if they can transfer, then they have made connections between abstract and concrete. So the methodology that I would plan for this would be a design experiment. And in the first phase, I would start with a small group, potentially 12, which would be 3 or 4 groups of 3 or 4 students, possibly up to one class of students, depending on how things panned out. But just to give these some of these things and to observe activity goes. The second phase would be the second iteration, would be to make some modifications based on the things we found in the pilot or small group study, and then to start looking at the learning gains of those students. And then in the phase 3 would be to start scaling it up to bigger classrooms to see, does it work in different situations, with different teachers. What are the classroom specific issues that we need to be investigated? So really, I'm only thinking about phase 1 at this point. And for phase 1, just the piloting of these things, I would want to do definitely want to do audio, video of group work and discussion, because we want to see evidence of mathematical and computational thinking, and that evidence is going to appear in their conversations, and it's also going to appear in their code, the documentation of the code, and their presentation of their code at the end. I'd also like to collect some interviews and reflections just to get another look at how computational thinking and mathematical thinking appear within the students, and also to track how their models evolve and how their thinking evolves throughout the course of the activity. And then we also want to have some tests of concepts and skills just to chart their progress and make sure that they are learning the math that we hope that they are going to learn. So in order to code for or measure mathematical thinking and computational thinking, I need to have some sort of benchmark or definition. And for mathematical thinking, I was thinking that I could use the Common Core State Standards for mathematical thinking, standards I referenced at the beginning of the presentation, and also the process standards from the NCTM principles and standards. I could code the conversations and interviews for evidence of those benchmarks. And then for computational thinking, this one's a little bit more tricky because the definition of computational thinking is so nebulous. But as a first try, I thought that the characteristics outlined in the NRC report would be a good place to start. Well, that's all I have, so I will leave you with this quote, which I think really sums up. I won't read it to you, but I encourage you to pause the video and take a second to read it. It's by Douglas Adams. And that's all. I look forward to hearing some of your feedback. Thank you very much.